Are you able to see this?
Yes. Thanks. Maybe you didn't press the share sound when you shared your screen. Maybe just stop sharing, just open the dialog again and check that ticker box, checkbox. Just stop sharing.
Uh,
Just stop sharing. Stop your screen share. Okay, press share screen again, but don't double click on your. Don't press OK. In the left hand corner, there's a checkbox.
I see it.
Share display sound. Okay, that's better.
Oh.
And away you go.
It's the kitchen.
Pi times r cubed.
Not really.
The equation v equals 2 4 over 3 times pi times r cubed is used to identify the volume of a sphere with radius r. And the equation s equals 2 4
Yeah,
times
for a
pi
second, I
times
thought
r
you were gonna
squared
win.
is used to identify the surface area of a sphere.
Guys,
Both
if you can't
equations are
talk, turn your
related
sound
as
off, please.
differentiating the volume formula results in the surface area
What's happened, guys? What's going on?
formula. This report aims to understand why one is the derivative of each other and, if possible, does the relationship between both equations hold in higher dimensions.
The accumulation of points is a line, the accumulation of a line is a surface, and the accumulation of a surface is a volume. The accumulation here can be regarded as an integral, and the derivation is the inverse operation of the integral. The first order derivative of the volume is the surface, and the sphere can be regarded as the layer of sphere surface accumulated from small to large. So the sphere volume is the area with respect to the radius after the derivation. For a sphere, every time the radius increases by a small distance, the overall equivalent is to increase the volume of a thin spherical shell. The thin spherical shell here is the surface of the sphere when it is thin to the limit. Derivation, integration, and differentiation are all based on the idea of limit. Utilizing the equation of a semisphere with the equation in figure 1, revolving this formula around the x-axis produces the volume of a sphere. Forming a disk with the height fx, the area of a semicircle produced in the graph is then seen in figure 1.1, and to find the volume we add these areas up infinitesimally, with the figure 1.2 being our final product.
The importance of a unit sphere is that any sphere of n dimensions or n sphere can be transformed and scaled into a unit sphere, henceforth allowing us to generalize the properties of a sphere down to a unit sphere. An n sphere described simply is a unit sphere with no definitive measurements. An n sphere is a topological space where topological space is defined as a pair xt, where x is a set and t is a collection of subsets of x. Topological space must follow the properties. The empty set is in T, X is in T, the intersection of a finite number of sets in T belong to T, the union of arbitrary number of sets in T belongs to T. An n-sphere is the same as a standard n-sphere. A standard n-sphere is the set of points in n+1 dimensional Euclidean space that is situated at a constant distance r from a fixed point. It is also referred to as the generalization of an ordinary sphere in three-dimensional space. To explain what an n-sphere is mathematically, it is defined as an n-sphere is a set of points in n+1 dimensional Euclidean space at a distance r from a fixed point C, where n is any natural number, r is any positive real number, and C is any point in n+1 dimensional space. N-spheres exist in topological space, and to calculate both volume and surface area for any n-sphere, it must be an n-ball. An n-ball is a space enclosed by an n-sphere and is considered closed if it includes the n-sphere, and open if it does not. Volume and surface area of an n-sphere that has radius r are proportional to the nth power of the radius r. The radius is considered to be capital R since there is no unit of definitive measurement. As an equation for an n-ball, refer to figure 3. From these equations, we can show that surface area and volume are related by the equation shown in figure 3.1. Then, from earlier, from our original equations, we have figure 3.2. So then we end up with figure 3.3, which can be rewritten as figure 3.4. Since the third dimension can be easily visualized, we will use n equals 3 for the third dimension. So, volume equals surface area over 3. The volume of a sphere in three-dimensional space is traditionally known as volume equals 4 over 3 times pi times r cubed, and surface area in three-dimensional space is surface area equals 4 times pi times r squared. Substituting values and removing r, 4 over 3 pi equals 4 pi over 3. We're able to remove r from the standard three-dimensional volume and surface area equations since it is in the topological space. Therefore, we have directly proved that for any dimension n, the volume of a sphere is equal to a surface area divided by n. This holds true for any dimension.
In this report, we discover the intricacies of how the equation of a sphere's surface area is related to its volume by differentiating the volume's formula to end up with the surface area. Understanding the stacking of infinitesimal layers of disks to create a bigger surface area. We can differentiate the curve to receive this because under the line or curve is the volume itself. Utilizing Frobenius theorem allows us to understand how we form the fraction 4 over 3 in the volume formula. A unit sphere is seen as a sphere with a center and a 1 unit radius. The importance of a unit sphere is that any n sphere or n dimensions can be morphed to get a unit sphere. We show how surface area and volume related on a multi-dimensions level through unit sphere and n spheres.
Okay, thanks guys. Thanks very much. Well done.